All right, we're going to continue in the second video on Chapter 8, which was about solids, liquids, and gases, but we're really just going to focus in on gases on this video. Ultimately, there's going to be a bunch of properties of gases that we're going to look at, because gases are just unique in that they have some properties that are measurable, like pressure and things like that. And the main thing I want you to learn is we're going to look at small laws, and then we're going to look at one called the ideal gas law. So we're really going to be able to do some calculations with the ideal gas law. But let's just get into the parts of a gas and focus on theories about gases first. Okay, so we're going to make some assumptions about gases, and that's basically just that helps explain the behaviors of gases. So the first one we're going to go over is called the kinetic molecular theory of gases. Okay, so they're listed on the next slide, but what you're thinking of is if we have a gas in this is a closed container. Remember, gas molecules are spread far out and they're constantly moving. So you have a particle that's moving and it might hit the wall, and rare occasions where they might actually hit other gas molecules. Okay, the energy of those gas molecules is not lost. In other words, the impact with the wall here would be elastic. When they collide, we don't lose energy. The energy is conserved. Okay, so let me show you the kinetic molecular theory of gases. So basically, a gas is a bunch of particles moving at random. They're constantly moving. There's no attractive forces between them. And in general, there's also a lot of space between the particles. Okay, so there's a lot of space between the particles, and there's much less space that's actually occupied by the gas itself. Okay, the last two kind of look at the kinetic energy. So the average kinetic energy is just proportional to temperature. In other words, if you were to raise the temperature of the container containing the gas, you would increase the energy, more particles would move around, they would just be moving faster, and so they would have potentially more collisions with the wall, so the overall energy in that box would increase. Okay, that's what the third one's trying to say. This fourth one is what I already said. Collisions are elastic, which basically means when the particles either hit the wall of the box or each other, the kinetic energy isn't lost. Overall energy is conserved, which we learned that in an earlier chapter. Okay, so let's look at the smaller gas laws. Before we get into them, we're just going to list a bunch out and go through them one by one. Before we get into them, let's get into some just concepts of the units that you're going to see and the variables you're going to see in these properties of gases. The first property is pressure. Okay, so just to be clear, pressure is just force over a specific area. So if these green spheres are the gas molecules, there's going to be some pressure exerted here when this one hits the surface at the bottom. Okay, and from maybe a physics class, force is mass times acceleration. Okay, so when you hear pressure, though, you're going to want to know what unit we're talking about. And there's a variety of units for pressure, and it just depends on what you're given. It depends maybe on the substance, what unit is most preferred, or where you're located in the world in terms of what unit might be more preferred. Okay, so you're just looking at this force over a certain area, and these are all of the units. Okay, you may have heard of the Pascal unit. This table, by the way, did not come from your book. Okay, you may have learned of the PSI, or pounds per square inch. Okay, so other units may be, you may see millimeters of mercury. Millimeters of mercury are actually the same thing as the torr. Okay, T-O-R-R, a little torr. Okay, and then the atmosphere. Okay, so 1 atmosphere equaling 760 millimeters of mercury would be given, like on the cover page of an exam or beginning of an exam or something. That would be provided for you as a known conversion factor. Okay, if millimeters of mercury and torr are equal, technically this unit on the right here could be torr, which is what this shows here, 760 torr is equal to 1 atmosphere, and sea level is 1 atmosphere. Okay, 1 atmosphere. So these are all units you're going to see. The most common one that we will see in this class is going to be the atmosphere, which is actually nice and simple. But if you were given a problem with millimeters of mercury and you needed to use atmosphere, you could do the conversion very easily, as long as you had this conversion factor there. Okay? So in addition to pressure, gases are often measured by volume. You're going to have volume. That's usually going to be in units of liters. And then temperature, just to be super clear, needs to be in units of Kelvin when we're actually working with it. So if you were given temperature in degrees Celsius, you would need to convert to Kelvin with the conversion we've already seen this semester. And the amount, if you were given in grams, you would need to convert it into moles. So the amount is usually moles of whatever the gas is we're talking about. Okay, so the gas laws are listed here. We're going to go through them. We've got these little ones here. We've got 5 smaller ones where certain of these 4 physical properties are going to be held constant, and then we say, all right, this is the relationship, say maybe between pressure and volume, or between volume and temperature, that kind of thing, okay? And ultimately we're going to get to the ideal gas law, which is the most important for the gases, okay? So Boyle's law basically says there's an inverse relationship between volume and pressure. So temperature, it's important here, temperature and moles are held constant. So ultimately what you're thinking of is I have a container of a gas. So this gas is maybe this green color down here. I have a container of a gas, and I'm trying to look at the relationship of pressure and volume. The temperature of the container and the amount that is in there in moles remains constant. Okay? So in this container, if the volume is 1 liter and I decrease the volume down to half a liter, what is that going to do to the pressure? If you notice, we have a direct, an inverse relationship. As the pressure increases, the volume decreases. Okay? So mathematically, that would say sort of the condition on the left would be like condition 1, the condition on the right is 2. So this is 1, this is 2. So mathematically, like if you were given the first pressure, the first volume, and the final volume, you could solve for the final pressure based on Boyle's law of P1V1 equals P2V2. Okay? So they are inversely related. If I were to increase the volume, say from 1 liter up to 5 liters, you should know that the pressure is going to decrease by the corresponding amount. It's going to decrease if I went from 1 to 5. I go up by a factor of 5. Pressure is going to decrease by a factor of 5 if I went that direction. Okay, so here's an example actually from scuba diving. So you actually, if you are scuba certified, you would know this law. You might not know it's called Boyle's law. Okay, so we have a scuba diver here on the right, and they're at the surface of the water where the pressure is 1 atmosphere. So that's their depth is 0 meters here. So they're right at the surface. Whereas way down around 20 meters, they're scuba diving, the pressure is 3 atmospheres. These arrows here are showing pressure of the surrounding water on that scuba diver. Okay, so if the diver holds their breath at the bottom and then they rise up to the surface, so they're done looking at coral or whatever they're looking at, and now they're trying to go to the surface, and the pressure is going down. So P starts at 3 atmospheres in condition 1, and so that's like P1, and then P2 is 1 atmosphere. So pressure is decreasing to 1 atmosphere. My question is, what is going to happen, according to Boyle's law, to the volume of air in the lungs of this scuba diver? If pressure decreases by 3 atmospheres, this is, like I said, if you're scuba certified, you should learn this, because you can't rise. You can't rise very fast when you're scuba diving, because what's going to happen? The volume of the lungs, if you went really, really fast, is going to expand by a factor of 3, which basically would kill your lungs. So that's why I have organ damage listed here, okay? Which is why you have to rise slowly so that your body can adjust to the new pressure, say from 3 atmospheres to maybe 2.5, and then a little bit higher to 2, a little bit higher in the water, lower pressure. Okay, So that's an example of Boyle's law. The next law is Charles' law. And here we have a direct relationship between temperature and volume that we're going to look at. And now in this case, pressure and moles are held constant. Okay, I want to make a note here. The temperature, I just want to reemphasize this, has to be in Kelvin when you're trying to do any of these mathematical examples. Okay, so on the left container, temperature is 200 Kelvin, and on the right container, temperature is 400 Kelvin. And so if I were to say raise the temperature, and maybe I didn't know what the volume would be, and this metal disc here could move freely in my container, okay? Once again, pressure is constant, like all the surrounding area, pressure is constant. The amount of gas is constant. If I raise the temperature, then you should know that the volume is going to increase proportionally to the temperature, okay? Direct relationships. So 200 versus 400 is basically doubling the temperature. What happens to the volume? The volume gets doubled, okay? And you could see that if you actually plugged in 3 of the 4 variables into this equation and solved for the unknown variable, you would observe the appropriate numbers that are given here in the example, okay? One of the things that students often confuse, a common mistake, is whenever there's a direct relationship, this formula down here that's comparing the 2 variables that we're talking about are going to look kind of like fractions, whereas on the previous example with Boyle's law, when there's an inverse relationship, remember it was just PV equals PV, you sort of multiply the 2 variables together that you're looking at and you're discussing. Okay, so here's an example with Charles' law. I've got a balloon, so we're going to have same amount of moles, same pressure, okay? And the balloon here is on the left sitting in ice water, and then I move the balloon to boiling water. The volume is going to expand, okay? So that would just be a nice, simple example of Charles' law where you could see, all right, the volume gets bigger. If I went the other direction, the balloon would kind of shrivel and shrink based on the decrease in temperature and the laws of Charles' law, okay? Here's an example calculation with Charles' law since I've just been doing other images here. So I have an initial volume, 2.57 liters, and an initial temperature. So you would have to convert that into Kelvin, and hopefully you could do it quickly. You could kind of round it to 273 Kelvin. What is the temperature if the volume has now been changed to 2.8 liters? So that would be your V2, okay? Now if you struggle a little bit with the algebra, and you have this formula here, it may be easier if you prefer to do what I have here kind of in the sort of maroon color, to rearrange the variables. We're solving for T2, and we have a new formula here, as opposed to plugging the numbers into the blue formula, and then maybe you mess up your algebra and you get lost and you get the incorrect answer, okay? So if you prefer, you could rearrange and solve for the unknown variable you want, so he's all by himself, and then plug in your numbers. It is entirely up to you. I'm going to plug in my numbers using the blue equation, but you need to figure out what works best for you and solve the problems in the manner that works best for you to get the correct answer, okay? So there's my V1 on top, T1 on the bottom, and V2 up top, and then T2 that I'm trying to solve for, and ultimately I get 297.6 Kelvin, okay? And that makes sense. If volume increased, temperature increased. Direct relationship, okay? The next law is Avogadro's law. It also has a direct relationship. So now temperature and pressure are constant, and moles and volume are in comparison. You're kind of relating moles versus volume. You can actually graph this really easily. So if I have number of moles on the x-axis and volume on the y-axis, you see it's a totally linear relationship, totally linear. If moles doubles, volume doubles. Everything is a linear relationship. There's a direct relationship here, okay? So another example, I have moles of a sample of helium gas and volume. So that would be my V1 and my N1. And then my question is, how many moles must be added to give 6.48 liters? So there's the formula in blue. Same process. I've got V1 up top, N1 on the bottom, V2, N2 on the bottom. So N2 should be 0.314 moles. Once again, if you struggle with the algebra, go ahead and rearrange the equation when it's still in like variable form and you don't have any numbers yet. Okay, so if you start to see, we've got a pattern going on. These are the three laws we just went through. Boyle's law has constant T and N, and this was where we had an inverse relationship between volume and pressure, and that's this representation here. This little sort of alpha symbol is supposed to be proportional to, related to, so volume is related to 1 over P, which is that inverse relationship that the slide said, and this was the formula given on the slide. Charles' law had a constant P and N, and V and T were direct. In Avogadro's law, V and N were direct in a constant temperature and pressure. Okay? So the next slide, if you see this pattern, the next slide we're going to go through both Gay-Lussac's law and the combined law all on one slide. So you should see the pattern here. In the top law, pressure and temperature, you have here, they are directly proportional, just like we saw the graph. But this earlier, this graph has temperature on the x-axis and pressure on the y-axis. Totally direct relationship. As one of them increases, the other is also going to increase. And that's why we get this blue formula here where we've got the fraction looking, so pressure and temperature. Pressure over temperature equals pressure over temperature. An example here, once again, volume is held constant. Moles are held constant, so you're looking at pressure and temperature. Okay, that's where you got to kind of, if you were given an image like this, you have to check and see what's constant versus what's changing. Okay, so if I increase the temperature, but the container can't change shape or expand in volume or anything like that, do you notice that the pressure increases? And that's basically because this rise in temperature is going to increase the collisions and therefore increase the pressure, that force that we were talking about at the beginning of the video. Okay, so that's what you're thinking of with this law. The last law, the only thing that's held constant is moles, and so it looks very similar to this, except you're just going to put the V right next to the pressure. Okay, so it's going to be like P1 V1 over T1 equals P2 V2 over T2, and I just put a 1 and a 2 to simplify it once in the numerator expression. Okay, and hopefully you've seen enough patterns to see you've got the same concept. You've got a direct relationship in P and T, inverse relationship with P and V. Okay, so I really want to look at the ideal gas law, which is gone over in section 8.10. We've got a table here with all the laws we just went through, and at the bottom is the ideal gas law. So you really need to know this. Memorize this formula, okay? And some people memorize it as PIVNERT. They memorize just PIVNERT. That's how they phrase it in their head, and on scratch paper they'll just write it out really quickly so they have their formula correct. When I was in high school, our rival high school was a school called Parkview, and so we memorized it is that Parkview is not our team, and that was how we memorized this equation. So what are all of the variables? You've seen pressure, volume, moles, and temperature, but R is something new. Okay, R is the ideal gas constant, and it has a known number, but it has 4 units associated with it. Okay, so you really need to know these units. You would be given R, the value of R, but you must be in the habit of writing your units when you're doing these calculations. Okay, so the units, if you see, you've got liters and atmospheres in the numerator and moles and Kelvin in the denominator. Now you're not always given it where it looks like a fraction. Sometimes you're given it where you've got this superscript -1. So remember that if something is in the denominator of a fraction, like the mole here, if I write it as a superscript -1, that means it's in the denominator. In Kelvin, same thing. Kelvin with the superscript -1, it is in the denominator. Okay, so just like Avogadro's number, you'll probably work with this enough that you'll actually have it memorized, the 0.08206 liter times atmosphere per mole Kelvin. But you would be given the value. Do you notice that all of the units correspond to the appropriate properties we just went through? Okay? So if you're going to be working with the ideal gas law, you need to be familiar with the unit. You need to make sure you use the appropriate units, okay? Like Kelvin for temperature, for example. So let's do an example. Once again, with this formula, if you're going to use it, you may want to rearrange it for the unknown variable that you're trying to find, or you could just solve it within the formula there if your algebra is strong, okay? So you're given moles of a gas, you're given pressure and atmosphere of a gas, and you're given temperature and atmosphere of a gas. And the question mark that you're trying to find is volume, okay? Calculate the volume of the gas, and these are the conditions of the gas, okay? I listed R over here on the right, and then the appropriate variables that are given in the problem. So what I did, if you need to check your algebra, is I did rearrange in this example for the variable volume that I'm trying to solve. If your algebra is strong, you can go ahead and just plug the number straight into the PV equals nRT equation, okay? Really, really, really be in the habit of writing out your units here. So you see how moles here is going to cancel with the moles there. This is just the numerator. And then Kelvin on the bottom of R is going to cancel out with the Kelvin in the temperature. So that 315 temperature there is the 315 right there, okay? In the denominator, because I have atmospheres on the bottom here, it cancels with the atmosphere in the numerator there, leaving me with the unit liter left from the ideal gas constant R, which is what I'm trying to find, okay? So the final answer should be 15.9 liters, okay? So there's another condition when we're dealing with gases that I want to talk about that is related to the ideal gas law, but it's called standard conditions, and that's a term chemists use where we say, I want to know across the world what kind of standard conditions could be that I could use to help compare gases. So it would be like, what are we going to say the temperature is? What are we going to say the pressure is? And I'm going to perform an experiment under standard conditions for a gas and compare it to standard conditions for another gas. So that shorthand is called STP, or standard temperature and pressure. Okay, STP. At STP, you're still using the ideal gas law equation, but moles is always going to be 1 mole. Okay, and pressure is always going to be 1 atmosphere, and temperature is always going to be 273 Kelvin, which is 0 degrees Celsius. Okay? So using the ideal gas law, the PV equals nRT, I just want you to see if we actually calculated the volume, you would calculate just like we just did the previous problem, and you would get 22.4 liters. So that is known as the molar volume of an ideal gas under standard conditions. That's the very top of the slide definition, okay? So there's an image from your book that's actually really, really good for this, okay? So you don't have to do this math. This is like a known number using the provided STP conditions. So if I've got 1 mole of a gas here, and this on the far left is O2, the molar volume is 22.4 liters. If I have 1 mole of helium, the molar volume is 22.4 liters. And it goes on for the other 2 examples, okay? So let's do a more complicated example of conversion, okay, because you can kind of start to see how we could get multiple steps of calculations that might be a little more difficult to solve, okay? And I tried to color coordinate this. So what we're doing is we're going to use STP, but read the question here. A gas occupies, all right, so we've got a volume, a pressure, and a temperature. What volume will it occupy under standard conditions? And I listed, just to be clear, in other words, at 1 atmosphere and 273 Kelvin. Okay, at what volume will it occupy? So in this case, you're actually not given 1 mole as the standard condition. You are saying, all right, I have this gas at a certain condition. You must solve the moles for this non-standard condition, and then say, all right, if pressure was 1 atmosphere and temperature was 273 Kelvin, what would be the volume for that gas? Okay, so I've provided the appropriate V1, P1, T1, and then the appropriate other conditions. Okay, and I kept the colors from the problem at the top, the same kind of blue and maroon color, okay? So here's the ideal gas law, here's the ideal gas constant with its appropriate unit, and just to be clear, the first thing we're going to do is get moles for this gas, and then determine the volume at standard temperature and pressure. Okay, so here I just rearranged the ideal gas law to solve for moles. Once again, if you're comfortable with using it in PV equals nRT, go right ahead and do that. Okay, 3 atmospheres times 10 liters given in the problem. There's ideal gas constant R times 300 Kelvin. So all those values are used, and everything cancels except moles. Okay, so that gives us the amount of moles. This number and the appropriate blue pressure and temperature can now be used in the same ideal gas law equation to solve for the volume it would occupy at pressure of 1 atmosphere and temperature of 273 Kelvin. Okay, so that 1.22 moles went there. Pressure is 1 atmosphere, temperature is 273 Kelvin. Once again, moles is going to cancel. Atmospheres cancels, Kelvin cancels, leaving me with liters, which is what I want. So 27.3 liters. Okay? So now that you've seen a bunch of examples with the ideal gas law and standard temperature and pressure, these are all of individual gases. I want to actually look at mixtures of gases. For a few more slides, we're going to look at mixtures of gases. Okay? So they sound really complicated, but when you see an image, you're like, oh, that's all it is. Air is a mixture of gases. Air has nitrogen and oxygen and argon and some other stuff in it, okay? So what you have is each individual component, each gas, is going to have its own independent pressure. So if that's true, we have something called a partial pressure, okay? And we have a new law called Dalton's law, where basically the total pressure in the mixture, the total pressure, so you might be kind of confused by this. Let's just say we have a gas that's the open circle gas and then the closed circle gas. So we got a mixture here. So we have an open circle gas that's going to have part of the pressure of the whole thing, and the closed sphere here, gas, is also a fraction or partial pressure of the whole thing. And if you added them together, the sum of the total, you would get the total pressure. That's all Dalton's law is trying to say. So an image of that would be if I have a container here with red gas and then a container with green gas, but then I combine them, I could have the pressure of gas A and the pressure of gas B. If the volume and temperature were the same here, if I put them in the same container, what will the pressure be in the container? The total pressure is just the pressure of A plus the pressure of B. This down here is Dalton's law of partial pressures. So it sounds really complicated initially, but it's not, okay? But if you're dealing with mixtures of gases, if we can do this with pressure with Dalton's law, we can do that also with the ideal gas law. So this is just pressure, the ideal gas law, PV equals nRT, rearranged for pressure to be alone on the left side of the equation. And this is Dalton's law, where we have total number of moles and then RT and V. Because they're all in the same container, RT and V are going to be the same for any gas in that container. Okay, so let's do an example, and we'll finish with this example, but it's kind of long. Okay, I have a mixture of 3 gases, helium, neon, and argon. 1 liter is the volume of the container. The pressure is 662, that's the total pressure. Temperature is 298 Kelvin. Now, this is a multi-step problem here, but I'm giving you the pressure of helium, that's a partial pressure, because that's one of 3 substances, and the partial pressure of neon. That's also one of 3 substances. You do not have the partial pressure of argon. So the pressure of argon we need in millimeters of mercury, because everything else here is given in millimeters of mercury, of just the argon. We do have the total, okay? So the first half of this, we haven't even gotten to that last question there, is to get the partial pressure of argon alone, because the next question is, what is the mass of argon? Once you have the partial pressure, you're going to be using the ideal gas law, PV equals nRT, and the appropriate other components that are given, like the 1 liter to solve for moles of argon. And from there, you can use the molar mass to get to mass of argon, okay? So let's just look at the beginning. This is just simple addition, subtraction to give us the partial pressure of argon in millimeters of mercury. Now, if we wanted to stop there, that would be fine. We could get the partial pressure, but you're asked to find more. And if you're going to use, on this other side here, if you're going to use PV equals nRT, remember R has pressure in atmospheres. So the first thing we're going to actually do is convert, using that conversion I talked about earlier, the millimeters of mercury into atmospheres, okay? So we're going to go to the next slide and continue this example, but we have a pressure in atmospheres, so we have that variable. We have a volume given at the top of the slide, so we have V. We need moles, we have R, because that's the constant, and temperature is given at the top of the slide, 298 Kelvin. Okay, so we should very easily be able to find moles and from there convert to mass. Okay, so this here was the plan that was on the right of the previous slide. Okay, so here's my rearrangement of the ideal gas law. Here's the atmosphere solved from the previous slide. And then the appropriate volume, ideal gas law, and temperature. Everything cancels except the moles. Now remember, if this is in the denominator and the denominator here, that puts it in the numerator for the final answer of argon, okay? So there's one more video in Chapter 8, and that'll just look at liquids and waters, but we'll stop this video for now. Thank you for listening.